Okay, so this video tutorial is designed to help you with the conservation of energy. So let's write out the conservation of energy, shall we? It is your initial kinetic and potential energy needs to equal your final kinetic and potential energy. Okay, so let's say, we've already touched on this, but let's review it again. Kinetic energy is given to you as 1/2 mv squared. Potential energy is given to you as mgy. Okay, so let's say that I gave you, let's see, let's say I gave you a graph that looks something like this. So we've got energy over here on our y-axis, and then we've got distance over here. Okay, and let's say the red line is total energy of the system. Well, we know that energy is neither created nor destroyed. So no matter where I am, okay, my total energy is going to be the same. In other words, you are going to have a flat total energy graph. Okay, now let's say that I give you a line that, let's go blue, that'll be fun. Let's say this line represents gravitational potential energy. Okay? So I'm going to try to make it as straight as I can. Imagine it's so straight. This is very difficult with a baby asleep on your chest. Now, there's gravitational potential energy. So the blue is PE, and then the red was total. Okay, so now we've got potential energy and total energy. Well, we have to have kinetic energy. And kinetic energy we will make green. So kinetic energy, let's say it works like this. It's going up in a straight line in kind of a flag pattern, if you will, here. Okay, and so let's think about this and think, what does this graph represent? Okay, so we start out with all potential and no kinetic. So if you think about that, you have all potential and no kinetic. Imagine this is the ground. Where does your object have to be? It's got to be up here. And it's got to be at rest because your initial kinetic energy is 0. Now, as we move a distance, the potential energy goes down and my kinetic energy goes up. In other words, the ball must be falling. So you can graph potential and kinetic energy and describe the behavior of an object. So let's say I've got another graph, and this is just a graph of potential energy versus height. So if I've got no height, what's my potential energy? Well, I have none. It's 0. And as I increase height, I increase potential energy. And I do so in a linear fashion because the equation for potential energy, it's up top, but I'll write it down here again, is mgy. There's no squared or anything, it's just mgy. So, potential energy increases with height in a linear fashion. Okay, so let's do an example of the conservation of energy. Let's say What do I want to do? Let's say I've got a ramp. And let's say this ramp is 150 meters tall. And I start out with, let's just say, a bobsled. Whee! And the total, no, let's make the ramp frictionless. So I want to know the speed at which the sled shoots out at the bottom of the ramp. So I start out from rest, and I want to know the speed. Let's go v2 at the bottom. This is an example of a type of problem where you're going to use the conservation of energy. So let's write it out again. KE1 plus PE1 equals KE2 plus PE2. So initially, I release it from rest. I've got no kinetic energy. And if I make this the ground, I've got no potential energy overall at the end. So my initial potential energy is given to me as my mass times gravity times my height. That equals my kinetic energy, which contains the variable I'm looking for, 1/2 m v2 squared. v2 being the speed at which it leaves the ramp. So to make my life easier, I can cancel mass on both sides because I have made this a frictionless ramp. So mass doesn't matter. So now that leaves me with gravity, which is 9.8, times my y, which is 150, equals 1/2 v2 squared. So you need to solve for v2. Okay? So that's an example of a type of problem where you would utilize the conservation of energy. Now, let's say that let's talk about kinetic energy for a second. And kinetic energy is, again, 1/2 mv squared. And let's say I double an object's speed, and I want to know what happens to my kinetic energy. Well, if you think about it, this new kinetic energy, I'll call it KE1, is 1/2 m, that stays the same, but now it is 2v squared, because it's double my speed. Well, that 2 gets squared as well, so KE1 equals, that becomes 4. So what if I made it 4 times 1/2 mv squared? It's the same thing, right? Well, this 1/2 mv squared is my original kinetic energy. So KE1, or the kinetic energy where my speed is doubled, is 4 times as big as my original kinetic energy. In other words, the speed, or the kinetic energy, quadruples. Okay? So, this problem right here will greatly help you on your test when dealing with conservation of energy.